I'm Calvin Seward. I work at Zalando Research, and I'm doing my doctor's at Johannes Kepler University in Linz. So I'm going to start off with a little introduction to Zalando. Then I'm going to talk about why I think neural networks are so powerful. Everybody talks about that they are powerful, but I think that there's a couple of reasons as to why they're powerful. Then I'm going to talk about two fun, non-classification related use cases, because everybody talks about classification, but I'm going to talk about something other than classification. First one is semi-supervised localization. Then I'm going to talk about generative adversarial networks, very popular these days. A lot of hype around papers that have been coming out of the Johannes Kepler University. We also came up with a GAN paper at Zalando Research recently. And then I'm going to finish up with the most important part of the talk. And so don't leave, don't grab the beer, it'll still be there, because the most important part is still yet to come. So, Zalando. So who's heard of Zalando? Yes, very good. Pretty soon it will be Google and Facebook and Zalando. We're operating in 15 different countries, 3.6 billion in net sales, 1,300 employees, 1,800 in technology. Yet again, if you want to become 1,801th employee, please talk to me. And the next two numbers are the important numbers. We have over 250,000 different fashion articles offered at any time, and we have 21 million customers on our platform. So the big question is, how do we connect that 250,000 of articles to the 21 million active customers? Because just doing the normal search of red dress in the top and then getting results at the bottom is not enough. And a lot of customers, they don't even know what they want. They just want to be inspired. They just want to browse a little bit and see what they can find. And so how to connect these fashion articles and these customers is why we came up with Zalando Research, because we want to be able to understand fashion and style. We want to be able to revolutionize the online fashion experience. And we want to use things like deep learning, statistical modeling, Bayesian inference to really bring fashion into the 21st century. And so we do this in 4 ways. We have product impact, we write papers, we come up with patents, and we do things like prestige. So we talk about how great our work is at conferences like this. We have about 12 different autonomous researchers, so everybody can decide what they want to work on. It's got to be fashion related, but you're very autonomous if you're in Zalando Research. And then all the buzzwords are there: big data, NVIDIA GPU, TensorFlow, yet again. So why are neural networks so powerful? So the classic feed-forward neural network is up here. So you have your input, you have your hidden layers, and you have your output. And we've got this nice little mathematical formula here. I think my first 3 slides will have more formulas than all the other slides combined, but whatever. So in any case, we've got this nice formula here where we take the input, then the input is transformed into linear space. That means we rotate it, we stretch it, we translate it with this B1, and so it's just this big linear operation that takes the input and does a linear translation. It's difficult when I have the microphone. And then we apply a nonlinear transformation, this sigma. And so this can be either like the rectified linear unit, or the exponential linear unit, or the sigmoid. And once we do this, we do the same game again, linear transformation, and then we get our output. So it's fairly simple what's going on. There's no huge black box, there's no real big magic going on. Just linear transformation, nonlinear transformation, linear transformation again for a fairly shallow neural network. Deeper neural networks, of course, you have a little bit more going on, but we'll see that the shallow neural network is already enough to have a thing to think about, because we can think of a lot of machine learning problems as learning a function. So most machine learning problems, they boil down to estimating a function that maps from Rn to Rm based on observations of this function. And so we observe x's, and we observe what the function is at those x's. So we can think of this as, for example, image classification. If xi is an image, then f of xi is its label. We can think of self-driving cars. If we have a sequence of images, that's our xi, And if then the sequence of image is red taillights at the end, then f of xi should be the action, should be applying the brakes. Because if that's not the action, the self-driving car, it won't drive itself for very long. And then we have recommender systems. So if we have xi as a bunch of customer shopping history, we want f of xi to be the next product recommendation that the customer will like. And so why do I talk about this, this paradigm? It's because the true function f of x won't be known, but we try and estimate it. We try and come up with this estimate, f of x hat. And so what does this have to do with neural networks? Well, neural networks are universal function approximators. So that means that for any function that fulfills a certain smoothness criteria, so it can't be too crazy, but for any function that fulfills this criteria, there exists a neural network that is arbitrarily close to this function f. And so the challenge is just to find the correct weights that would give us this function. And then with the correct weights, we can do stuff like this. We can take an image and come up with its label. So it's all about just finding the correct weights. And this already holds for this simple neural network here. It just has to have one hidden layer, and we can already get arbitrarily close to any function, as long as it has enough hidden units. And so knowing that there exist weights isn't very helpful if you can't find them. And so that's another great aspect of neural networks, is that you don't have to do some sort of a grid search, which would take forever, but we can easily differentiate the neural network. And we can easily say, what is the error, what's the derivative of the error, so how far off we are, with respect to each individual weight. We can easily calculate this for every single weight. And then, so calculating this is known as backpropagation. And then, once we know this, we can take this differential here, and that gradient, we can take this gradient, and it's going to point in the direction that decreases the loss the fastest. So, we have a universal function approximator, and we know where we have to move the weights in order to decrease the loss for a given training example. So we put this together, and we get this basic training algorithm called the stochastic gradient descent algorithm. So we start off with a learning rate, and then while we still haven't lost patience, we keep on doing this. We take a training example from our training set. We calculate the error of that training example. And then once we have that error, we do this gradient trick that we were just talking about. And we calculate the gradients that we have to apply to the weights. So these updates we have to apply to the weights. We apply them to the weights. And slowly but surely, we get weights that fit the data very nicely and reduce this error to where our f hat of w is close to the true f. And then at the end, we get this trained neural network. And so the beauty of this is we see that it only has to load one training example at a time. For efficiency, we use mini batches, but it works for one training example at a time. It's not like other algorithms like SVM or whatever, where you have to keep track of quite a lot of training examples at the same time. But here, it scales very nicely with the amount of training data you have. More training data is not more problems. And so if we put it all together, we see neural networks are a universal function approximator. We have this gradient business to where we know how to update them. It scales well with the data. And lastly, it can all be done in parallel on GPUs. So that means that we can use the fastest computer architecture that's available to us, or also TPUs, I guess, are now the fastest. We can use the fastest computer architecture that's available to us and apply it efficiently to this problem. So I think that honestly, if you have another algorithm that can combine all these four aspects, it would also work fairly well. But this is what we've got. And so neural networks are sort of magical these days. But there's a reason for this magic. So I'd like to talk about a fun use case that's not classification related. And we call this semi-supervised localization. And so what we can do with the machine is we can get the machine to tell us where things are on a picture. So we can ask the machine, where is the pullover, where are the boots, where's the trouser, where's the shirt? And it's able to show us more or less where it is. Everybody thinks, okay, you guys aren't impressed. But the impressive thing is we've never told the machine where things are. We've never, ever given it any localization information. It's learned the localization information all by itself. So this seems a little bit magical, but there's a simple explanation. And so we do this by leveraging this data set, the so-called shop to look data set. So if you're on the Zalando website, if you've never been there, I can highly encourage you to go. And you see this wonderful, wonderful pullover here. And you say, it's discounted, but it's not exactly my color. But these boots, I love the boots. And you want to know where you can get the boots. Then you can hit this shop to look feature, and you get to a page like this, where you see the different articles that are on the picture. So we see the pullover, the shirt, the boots, the pants, and we also see some things that are not on the picture, but these are things that would go well with them, because this handbag... Yes, it would totally go well with the boots. So in any case, to make this work, we have to have this fun data set, and we call it the shop to look data set, where we have a bunch of different fashion articles all on the same picture, and we know which ones are on that picture. And so we know that it's this guy, the shirt, and the pants. They're all in the picture. And so we can then take this data set and use this method that was outlined in this paper here, deep learning for discriminative localization. And we can train a classifier with a specific architecture, and we'll get to the architecture. But the idea is that we train this classifier, and it should give us an output that's close to this. So it should give us an output that's close to this 0, 1 guy, where the ones codify the articles that are present, and the zeros codify the articles that are missing. So for example, here in this picture, pullover, ankle boots, trouser, those are present, but bikini, sunglasses, sports shirt, those are missing. And so the zeros are what's missing, the ones are what's there. And once we train this classifier, we see, okay, the classification performance is pretty good. It looks at this picture, it shows us trouser, low shoot, bag, shirt, but we're not talking about classification today. So the key for why this works is, one other little trick is we use the pre-trained Google Inception network. Using pre-trained networks really is helpful because it makes it to where all the weights and whatnot are already learned, and it already from the get-go sees useful features in these pictures. And it looks like this. And the key here is that it's completely convolutional. Every layer is convolutional. So then the results are pooled with average pooling. We have one last fully connected layer, and then we get our classification output. And we use the sigmoid cross entropy loss to tell how close we are to what we should actually be getting. And get this loss, we backpropagate it back. We talked about the backpropagation a little bit earlier. So you ask yourself, why is he talking about this architecture? And the deal is that this localization that we get for free, is in the architecture. The key is in the architecture. And the key is that this last little bit here is entirely linear. So it's an equivalent to an ensemble of classifiers, where each classifier takes all the channels of just one part of the image. So this last convolutional layer, what it is it's telling us what features were learned for a certain part of the image. And then the next part over, what features were learned for another part of the image. Then the next part over, what features are learned for that part of the image. And so for each part, you train a new classifier. It's mathematically equivalent for each part training a new classifier. And then averaging these classifiers to get your prediction. So then by doing this, it makes it to where we are able to get the localization without any prior information, which is really cool. And so here, you can see it on the picture very nicely. So we've got basically a bunch of different classifiers trained, or the same classifier trained that just looks at different regions of the image. And here, it looks all over the image, and up here it says, okay, I'm looking, I don't see a bag, I don't see a bag, I don't see a bag, don't see a bag, don't see a bag. Oh, look, there's a bag over here. And it says, oh, wow, there's a bag, and it lights up in this area. And so we get localization information. Here's the bag, here's the shirt, here's the shoe. It doesn't work very well for trousers because this button up the front shirt, we don't have a very good assortment for the Scottish audience, so we don't have very many kilts. Whenever I make a joke, there's always something going off. So we don't have very many kilts. So whenever the computer sees a shirt, it always knows there's going to be pants at the bottom, and so that's why it thinks that these are pants, these are trousers. Then it works very nicely for this lady here. Here it doesn't work so well because the shirt is covered up, so it doesn't find the shirt. But overall, it's really cool that we're able to leverage this data set to find where things are on the picture without ever telling it, without ever having anybody go through and classify the images, or not classify, but segment the images and say, this is this is that, this is that. So that's a really cool and exciting way that we can leverage our data. The next thing that I want to talk about is generative adversarial networks. A lot of hype around GANs, so I want to quickly outline how this works and show a couple of examples. So we get back to the idea of neural networks being a universal function approximator. So if it's a universal function approximator, then there must exist some sort of weights, WG, such that if Z is some multivariate random noise, then G will map from Z to cat pictures. So it'll be able to take some random uniform noise, look at this random uniform noise, and transform it into a picture of a cat. All right? There must exist some sort of weights to where this happens. But the trick is to find these weights. And the trick is to find these weights such that these two measures of quality are fulfilled. First of all, we want the images, the generated images, to be very convincing looking. They should look exactly like cats. And the second thing is there should be a very large diversity of images. If it always generates the same couple of cat pictures, or it only generates black cats but doesn't generate white cats or tabby cats, then that's no good. So then the question is, okay, how do we evaluate G with respect to these two measures? How do we evaluate G to where we know that it's generating good images and generating diverse images? And so this idea of using networks to generate images, this is nothing new. It was already done with restricted Boltzmann machines. There they generated these sort of MNIST-looking images. But there also, how do you evaluate the quality was something of an open question. So whenever you have a problem with neural networks, a lot of times the solution is another neural network. And we know, okay, neural networks, universal function approximators. So there must be a neural network D that has weights WD, such that if we give it a picture, it's able to spit out a 1 if it's a real cat picture, and it's able to spit out a 0 if it's a generated cat picture. All right? So this thing must exist somehow. What the weights are, we'll get to that in a second. And then, if G creates a poor quality image, D will be able to detect it. And if G fails to create diverse images, our discriminator, D, will be able to detect that, oh, it's only generating black images, black cat images. It should be able to discriminate lots of other, it should be able to generate lots of other images. And then the last trick here is that if we put the two together, if we have G of Z of D, this is also a neural network. So we can use all this gradient business that we've been talking about to update the weights of G, of our generator. So this inspiration leads us to the classic formulation of generative adversarial networks. And so, I know, it's sort of a complicated formula, but the idea is fairly simple. What we're doing is we're playing a minimax game. We're trying to first find a D that maximizes this whole thing. So D is our discriminator, and D should be able to tell, to look at the real data and say, oh wow, this is real data, we'll give it a 1. And D should be able to look at the generated data and say, wow, this is generated data, we'll give it a 0, and separate the real data and the generated data from one another. So if it's able to do that, then this guy will be maximized. But it's the minimax game. So the minimum part is G. So the G, the generator, is going to try and fool the discriminator. And G will try and minimize this whole thing by generating data that the discriminator thinks is real data. So this is what we're trying to achieve. And we do this with this little algorithm here, this GAN training algorithm. So we start off, and yet again, as long as we haven't lost patience, we just keep on going. And we train our discriminator for a couple of steps. We generate some random data, we have some real data, and we train the discriminator with our gradient update step to try and discriminate between the good, the real, and the generated data. And once the discriminator is trained a little bit, we update, we sample a noise vector, and we update this guy here. We update the weights of the generator so that it fools the discriminator. And this update works very nicely since this whole guy is a neural network, and we can use this back propagation technique to come up with the updates of the weights. And so this works fairly nicely. So we can, for example, use GANs to generate creepy faces. I don't know if you guys can see it in the back, but these faces, they look somehow very crisp and very, very clearly faces, but they're also very clearly a little bit off and a little bit creepy. So my slides, they're already online. You can look at them if you want. We can also use it to generate fashion. This is quite a lot of fun. We have a latent fashion representation, and for each article, we train it to take this latent representation of the article and generate the picture of the article. And then we take two random latent representations, for example, the latent representation for this shoe and the latent representation for this shirt, and we then interpolate in this latent space and get the generator to generate the associated image for each spot in the latent space. And then we go from shoe to, I don't know, and then it sort of looks like a shirt. And everything in between, it all looks very fashion related. But it manages to smoothly go from one fashion article to the other. Also really interesting, if you go from dress to shoe, it actually creates handbags in the middle. Another thing we're really excited about is generating textures. So this was some work that was published by colleagues of mine where they generate this snakeskin texture. And each corner is a different snakeskin, and they're able to interpolate between the different snakeskins. And the stuff in the middle looks very natural, also looks very snakeskin-y, but interpolates very nicely. And these textures can be as large as you want them to be, and they look very visually pleasing, very natural. And so it's a very, very exciting paper that they came up with. But there's a lot of open questions and a lot of problems with GANs. And so I would say that the main thing is convergence is the exception, not the rule. And if you play around with GANs, it seems like a lot of very successful GANs, like DC GAN, have been highly tuned. And if you change a good bit of the parameters, then all of a sudden it does something completely different, which is really frustrating. And so finding the right parameters, it seems to be a real trial and error thing. And what can be especially frustrating is this problem of sudden divergence. Sometimes you'll be training, and whatever your fit score or whatever metric you're using to evaluate, it'll go down and down, and it'll be going down, and you're like, oh, things are going very nicely. And then, bam, it'll jump up and it'll never go down again. And you're just like, oh, this is so frustrating, you know? You start it in the afternoon, you watch it go down, you're like, okay, everything's going good. I'm gonna get lots of citations for this great paper, you know. You go home, you come back in the morning, you make your coffee, and you look at it, and it's like doing terribly. Oh, this is so frustrating. But this is sort of the rule. It's been my experience. And GAN convergence is really sensitive to things like learning rate, activation functions, the generated discriminator architecture. I think it's also very sensitive to the alignment of the stars. I haven't seen any peer-reviewed stuff on this, but this is my gut feeling. And so it's a big open question. If one of you guys is able to come up with a way to make GAN convergence the rule and not the exception, you will be very famous in the machine learning community, I can guarantee you. And so that's not the important part of the talk. This is the important part of the talk. And I thought, you know, since it's a meetup and there's a very diverse group of people here, I want to talk about something that's a little bit different from just the nuts and bolts of machine learning. And so there's this great book called The War on Science by Sean Otto, and he outlines this process that new technologies go through a lot of times from discovery to acceptance within the society and the regulatory framework that sort of governs this new technology. And he talks about, it starts off with discovery. So a new process or tool is discovered, and it could be like a chemical, for example, like DDT is a great example. The insecticide that got rid of a lot of mosquitoes. It solved a lot of problems. Mosquitoes caused a lot of problems, but it created a lot of problems too. Nanotechnology, genetic technology, internal combustion engines, fossil fuels. And these things, they vastly expand utility, power, convenience, and efficiency. And then, once it's discovered, it's applied. And there's a lot of applications that come out. They're developed, they're commercialized. It increases productivity, lowers cost, does a lot of great things. But the scientific understanding of the aspects, it oftentimes lags behind. The scientific understanding of the impacts oftentimes lags behind. Then we have development. Industries grow up around this technology, and they make a lot of money. Investors, they invest a lot of money. A lot of people, they want to make a lot of money off of this. And then sometimes you have the boomerang. So what happens is a tipping point is reached in which the application has noticeable negative effects on health or the environment. And then, fueled by public outcry, scientists study the degree to which these things have an impact, or maybe even a bad impact. This leads to a battle. Regulations are proposed to minimize the negative effects, but vested interests, they fight. They discredit the science, they discredit the scientists, they try and act like there's other reasons for this to happen. And so think the climate change debate. There's still a lot of, especially in the United States, there's still a lot of people out there pushing wacky theories as to what's causing climate change. And then this battle ensues between the old science and the new science. And so a lot of times this reaches a crisis where the cause and the effect of these problems it's undeniable, and it leads to public scrutiny and outrage. And finally, the politics are tipped in the direction of reform. Then you have adaptation. You have regulations that are passed, or societal norms change, usage of the technology changes, and things sort of adapt to a more sustainable trajectory. So my question for you guys is, where do you see artificial intelligence here? And not just artificial intelligence, but the whole ecosystem surrounding artificial intelligence. In order to have artificial intelligence, you have to collect a lot of data. In order for artificial intelligence to make money, you have to roll it out and have people interacting with agents making decisions, oftentimes agents making life-threatening or life-changing decisions. So I wonder where is artificial intelligence here? And it can be a lot of places. And we just talked about this, this new data protection rule. And it seems like, okay, adaptation is already part of it. And the other question is, how can artificial intelligence become a part of society in a beneficial way? So that artificial intelligence is something that really benefits us, makes our lives convenient, without some sort of Skynet Terminator catastrophe. And the answer to both these questions are both political and scientific. You have to understand the science of how artificial intelligence is made, how neural networks work, how training data works, in order to come up with effective strategies to answer these questions. But you also have to answer political questions. Is it okay if dermatologists all lose their jobs because the computers are better at diagnosing skin cancer? I don't know. It's a political question. And so what I want to ask you guys is how can you bring science into this political discussion? Because you guys, as scientists, you know so much about how this works. But oftentimes, I feel as if science isn't at the forefront of a lot of political debates, even though a lot of political debates are caused by scientific problems. Problems like climate change that are caused, it's a technologically driven problem. And we see in the numbers that scientists somehow aren't quite as involved as they could be. If we look at how the subjects that were studied by people who are in the Bundestag, sorry, I didn't have the Austrian data, I only have the German data. We see this tiny sliver up here. 11.2% of subjects studied were natural sciences or medicine. The vast majority is law, governance, liberal arts, or arts. And so you've got to ask yourself, why is this? And how is it that we as scientists can come away from just thinking about what's the next app going to be, what's the next product going to be, what's the next startup going to be, what's the next paper going to be, but we can start about thinking, how can we contribute to our society to where our society ends up being a society that we want to live in the future? Thank you.
Thanks a lot, Calvin.
Thank you.
Let's get to the difficult part, to the question. Please bear with us. We do like two questions.
There's lots of beer outside, by the way.
Okay, let's do the top two questions here, if it's okay for you. We can look here.
Okay, what are you using the localization information for?
See it here.
So one thing, there was we haven't used it yet, but there were quite a few different things that we thought of. And one is this app where you can take a picture of somebody. And so unfortunately, Thomas is a bit of a bad example because his outfit is so generic. But in any case, assuming he were to have something interesting on, we could take a picture of him and be able to say and be able to get recommendations as to what is in the Zalando shop that's similar to what he has on. But in order to do that, we have to understand where the different articles are on the picture, so that we can sort of draw bounding boxes around the different articles, and then the customer can click and say, oh yeah, this article, this one's interesting to me. Tell me more about that. So that's one use case.
Luckily, you don't have these nice AI shirts on Zalando yet.
We're working on it.
Let's take that bottom question there. If you never told the computer that this thing people holding in their hands is called a bag, how can it know?
Okay, it got the labels. But it didn't know where it was. So it was the localization of where the bag was that the computer learned all by itself. But it got this. If you remember this this vector that's zeros and ones, that was sort of fed in as training data to show the computer, okay, this is what's present. This is not what's not present in the picture. Yeah, sorry if that wasn't clear.
Good that we clarified it now. Final question. Let's take the third one there. How much effort do you put into data preparation at Zalando? Did you bake your requirements into data gathering?
Okay, yeah, I mean, you could definitely spend a whole session talking about preparing the data and getting the data ready. And so it really depends. It really depends on the sort of area of Zalando you're working in. And some areas prepare the data very nicely, and some areas don't. And in data preparation, it's not like you have a data preparation team. But if you have a front-end developer, and you're trying to figure out how the customer is interacting with the app, then he's got to program in a pixel to see when a customer is swiped from one image to another, because the images, they're all preloaded within this single page app, and so this swiping from one image to another, it doesn't send an HTTP request to the back end, but you have to log it on the front end. And so if that guy gets lazy, he's like, this data preparation, this is my job, it's got to just, releases, or he changes stuff, then all of a sudden your data pipeline is broken. So there's a lot of stuff that goes into having a clean understanding of what's happening throughout the entire company. So yes, I would say a lot goes into it, but it's not my job.
Good. Thanks for clarifying this. Let's thank Calvin again. Big thank you.